Okay, AP Chem kids, I want to do a video on strong acid titrations with a strong base. And what we make is something called a titration curve. It's also called a pH curve. And you'll know it's a titration because you are measuring pH is on the y-axis and the volume of your titrant is on the x-axis. So what I want to kind of start out with and talking with here with pH curves is I want to just point out is that typically you have a beaker and you have in here is your burette, and in your burette you might have something like a strong base like sodium hydroxide, and what you have in your solution might be something like a strong acid like hydrochloric acid that completely dissociates. What you'll be doing is you're going to be measuring, so I'm going to put a pH meter here. So you're going to be measuring the pH as a function of adding this sodium hydroxide. So as you're increasing the amount of sodium hydroxide, the pH is going to change. In a strong acid and base titration system, you get a curve that looks like this, okay, where halfway to this inflection point of where it's straight up and down, if you go half that distance, which is right at about here, that is called the equivalence point. And the equivalence point is when the moles of H equals the moles of hydroxide. So that's what we know from our first year course. What you will need to kind of tune into is that there are other types of titration curves. They just don't look like this one here. There's other pieces to it, and you're going to hear about them in another video as well. So let's though kind of get talking about our strong acid, strong base situation. The other thing that I want to point out before we start with the calculations of how you do a strong acid, strong base is I want to talk about the idea of a millimole. And a millimole is really a millionth of, or I shouldn't say a millionth, a thousandth of a mole. So just like a milliliter would mean a thousandth of a liter, we can use the term millimole. And what that does is that when we take a millimole and we divide by milliliters, we get the unit of molarity, which is also the same as moles per liter. So a millimole per milliliter would have the same molarity value as if it was in moles per liter. And why we want to do this is it's a lot easier to deal with a number that's in millimoles per milliliter than always typing out a really small number or something that's times 10 to the negative 3. So that is preferred when we are talking about acid-base titrations, because typically we're dispensing in milliliters, and that is what it just makes that easier to calculate the molarity. Okay, so the first thing that I want to talk about, and this is a case study, this is also in your textbook that you can follow along with. You also should have a handout that you can follow along with and put in this information. What we're going to do is we're going to start out with, so what I'm going to start out with here is a beaker of nitric acid. So in my beaker, I have nitric acid, and so that's a strong acid. So it's going to completely dissociate into the hydrogen ion, and then that is the nitrate ion. And what we're going to be adding to this is NaOH. Okay, so sodium hydroxide is going to be added to the strong acid. I want to calculate the pH along the way as I'm adding sodium hydroxide. The first thing we're going to do is look at what would be the pH. So I have a pH probe, so consider a pH probe being right here into the solution. And what if I asked you guys what is the pH of the solution? Well, you think to yourself, well, what are the major species that are in this beaker? It's hydrogen ions and that should say, I see that I have a typo here, so I'm just going to cross that out. That should have nitrate ions, not the nitric acid, because that stays together. That doesn't stay together, it's a strong acid. So it's hydrogen ions, the nitrate ion, and you should have water. And what's going to happen is that, as we talked about, nitric acid is a strong acid, so it completely dissociates. And if we have 0.2 molar of the sodium, or of the nitric acid, we would have 0.2 molar of the hydrogen ion. So calculating the pH for that solution before any NaOH is added is really relatively simple. You just take the negative log of the 0.2. Now, what happens if we have this solution and now we've added 10 milliliters of sodium hydroxide and we need to calculate the pH? Well, because this is a strong acid and a strong base, what you need to recognize is that the H from the nitric acid and the OH from the sodium hydroxide, they completely dissociate in water because sodium hydroxide is a strong base. Nitric acid is a strong acid. So the hydrogen from the nitric acid and the hydroxide from the sodium hydroxide are going to get together and make water. So this is the major reaction that happens when you're talking about a strong acid, strong base titration. But what you need to do is you need to consider, after you know, how much hydrogen you have before you added the sodium hydroxide. And then once the sodium hydroxide is allowed to react, how much water in essence will be made? How much of this hydrogen will be consumed? So I'm going to take a look at this 50 mils. The concentration is 0.2 molar. As you can see, I have that right up here. So that makes 10 millimoles. And I also am adding 1 millimole of hydroxide because I've got 10 milliliters of my sodium hydroxide, and its concentration is 0.1 molar, so that would be 1 millimole. Now, the reaction is allowed to happen, and what would happen is that this OH is going to react with the H to make water. And what will happen is 0 millimoles of OH will be left, because this is what we would call commonly the limiting reagent. Okay, and what is going to happen is that if 1 millimole of hydroxide is consumed, that means 1 millimole of the hydrogen ions consumed to make that water. So you have 9 millimoles left. With those 9 millimoles left, then you have to consider the concentration, right, of the hydrogen after you've added the 10 mils of water here. So once you've added this 10 mils of water and you got 10 mils of sodium hydroxide and you got 50 mils of nitric acid. So now what we're looking at is that I have a total for the hydrogen ion concentration, a total of 9 millimoles, and I have 50 plus that 10. So that makes this hydrogen ion concentration 0.15. With that hydrogen ion concentration being 0.15, I can then calculate the pH, as you can see right here on the right-hand side. And the pH for that solution becomes 0.82. So I then plot that point on my titration curve. Okay? When we look at adding 20 mils total, the process is going to be the same. So I am going to I'm just going to open up the slide here and I'm going to hit pause. I opened up the slide and I'm going to hit pause. I'm just going to give you guys a few minutes to take a look at the logic of what was going on here, just to save time on the recording. Okay, so you can see that after we add 20 milliliters of the base, 8 millimoles of hydrogen ion is left. That gives me a concentration of 0.11 molar, and the pH becomes 0.942. And so if I were to add this here, you know, it would still be maybe a point right about here that pH would be. Okay, so it didn't change significantly. Similar now, what will happen when I add 50 mils? Okay, this would be the same process as before, just like we did before, and the pH, you can see, just slightly rises to 1.301. Now, when we are adding a total of 100 milliliters of 0.1 molar, when at this point we are at the same amount of NaOH and the same amount of HNO3 in terms of millimoles. So the millimoles will be the same. So you can see here the amount of sodium hydroxide is 10 millimoles and the amount of nitric acid is 10 millimoles. So do you know what that means we are at? When the moles of OH and the moles of H plus are the same, that means we are at our equivalence point, or it's also called the stoichiometric point. So enough NaOH has been added to the titration to react exactly with all of the H plus that is there. And when we look at that, that becomes a very sharp point that it just very quickly jumps up. That's our equivalence point, okay? Now, here's also an important piece to know, is that since the sodium ion or the nitrate ions have no acid-base properties, the pH is controlled by this piece right here. The pH is controlled by the water. So that means the pH is 7. This is only true for strong acids and strong bases, that at the equivalence point you'll be at a pH of 7. As you'll see in videos later on when we talk about other types of curves, you're going to see that that's not always the case, that the pH at the equivalence point is 7. It's only true when you're titrating a strong acid and a strong base. So now, what will happen if I keep adding my base, and I'm at a total of 150 mils added totally to that 50 mils of 0.2 molar nitric acid, okay? Now, as I look at what's happening before the reaction, I still have the same amount of acid. Notice how that's staying constant, but I'm adding more OH. And as I'm adding more OH, you'll notice that now the OH is in excess, okay? And the hydrogen ions all consumed. It's the limiting reactant. Now the OH is in excess, and when the OH is in excess, you will notice that you have to find the concentration of OH, and you have to calculate the pH. In this case, I used the KW equation to get to the pH, but you could go the other way too. You could find the POH and then subtract from 14. That would work as well, okay? And finally, if we were to continue and add 200 milliliters of NaOH and calculate the pH, the process would be the same as the previous page for the NaOH. And the pH, notice how it didn't change significantly. That's 12.60. So when we take a look at the points that we've plotted for this strong acid and we kind of add these together, you'll notice you get that typical kind of pH curve. And that was kind of hard to do with my drawing, but that's pretty much how it looks like. You get this really big, huge inflection point. Half that distance is roughly where you are at your equivalence point. Okay, so you may want to go back and maybe pause some of these slides because I did have to go through this very quickly to make it within that 15-minute time frame. But you should be able to calculate these and have a handle on predicting the pH anywhere along the building of this titration curve. That's an important aspect, okay? When it's a strong acid, strong base, you should be able to predict the pH knowing how much base you put into the acid. So I would recommend maybe going back and looking at these slides again. In the next video, we're going to talk about a weak acid with a strong base titration. And that's a little bit more involved. So watch out for that, and that's coming up next. I hope this video helped, and good luck.